So now let's look at problem number 6. So the problem states, how many positive 4-digit integers have only even digits and are divisible by 5? So it's basically a counting question, and one of the key clues over here is they're asking for only even digits, but the number also has to be divisible by 5, meaning that the last number must be 0, because the only numbers that are divisible by 5 are numbers that end with either 0 or 5, and since 5 is not an even number, the only option left is 0. So let me just try writing the number as something we can write as something like x, 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 and then 0, where the x's denote different digits. So we see here that we still have 3 spots to fill, and the options for those spots are 0, 2, 4, 6, and 8. And since there are 5 options, you may be tempted to say that there's 5 times 5 times 5 different options that we can choose from, but that's actually wrong, because if we were to do something like 0 and then 2 digits and followed by 0, that wouldn't be a 4-digit number anymore. That would be 3 digits. So for the first number, which is the first digit, we must choose something from either 2, 4, 6, or 8, and for the other 2 digits, we're okay with choosing anything from 0, 2, 4, 6, 8, and same for this other third digit over here, 0, 2, 4, 6, 8. And that leaves us with a total of 4 times 5 digits over here, 5 times 5 different possibilities, and that's equal to 100 different positive integers that satisfy this condition over here. So that's our final answer, 100 positive integers that satisfy the condition over here. So now, let's look at problem number 7 from this test. So we see that the 25 integers from -10 to 14 can be used to form a 5x5 box where the sum of every row, column, and main diagonals are the same. And what we're asked to find what the value of this common sum is. So, in order to do that, let's just try drawing a box. Let's just try drawing a square over here. So, this square can be broken up into 5 parts. So this is a 5x5 square over here. And without loss of generality, if we look at every single one of these rows, it must mean that since there are 5 rows, it must mean that the total sum of all the numbers in this box divided by 5 must be the sum of each individual row. So what is the sum of all the numbers over here? So that's going to be -10, -9, -8, all the way to, and then 0, and then +1, +2, all the way to 14. So the -10 cancels out with the +10, -9 cancels out with the +9, etc. And this just leaves us with 11, +12, +13, +14, which is simply just 50. So 50 is the sum of every single number in the box. And now when we divide that by 5, 50 divided by 5 is 10. So the sum of each row, each column, and each diagonal is simply just going to be 50 divided by 5, which is simply just 10. And that is the sum that we were asked to find. So now let's look at problem number 8. So it's just asking us what the value of this expression over here is. 1 + 2 + 3 - 4, +5 + 6 + 7 - 8, and all the way to 200. And you see that this is grouped in terms of 4. The pattern repeats every terms of 4, so it's three numbers being added together and then subtracting the next number. So let's just try rewriting it in terms of groups of 4. So 1 + 2 + 3 - 4 is 2. And then +5 + 6 + 7 - 8, that's going to be 10. And then the next one is going to be +9 + 10 + 11 - 12, and that's going to be 18. And all the way to the end over here, 197 + 198 + 199 - 200. And that's basically 394. The number is 394 for that. So you see here that this is an arithmetic sequence with a common difference of 8. And in order, all we have to do now is just find the sum of this arithmetic sequence over here. And we know that there's 50 terms because we're grouping them by 4, and the last term is 200. So the number of terms must be 200 divided by 4, which is 50. And since we know the number of terms, we can just use the formula for finding the sum of an arithmetic sequence. And the sum of an arithmetic sequence can be written as the number of terms, which is 50, times this times the first term plus the second term, so 2 + 394, divided by 2. So this can be written as 50 times 198, and that's going to be the same thing as 9,900, which is our final answer for finding this value of this expression over here. So now let's look at problem number 9. So the problem reads that a single bent section can either hold 7 adults or 11 children. And when n bent sections are connected, an equal number of adults and children will occupy the same bent space. What is the least integer value of n? So the first thing to notice is that they're asking for an equal number of adults and children. And that means all we need to do is to find the lowest common multiple of 7 and 11. And the LCM of 7 and 11 is simply just 77. 77 because 7 and 11 are co-prime, and that therefore we must multiply these two numbers together, so it leaves us with 77 as the LCM. And now to figure out how many bent sections we need. So since there's 77 adults and 77 children, we're going to need benches for both of them. So for 7 adults, if there are 77 adults, we will need 77 divided by 7 bent sections for the adults. So 11 benches for the adults. And if there are 77 children, and 11 children can fit for bench, that means we must do 77 divided by 11 benches for the children. And 77 divided by 11 is simply just 7. So it leaves us with 7 benches plus another 7 benches, which is equal to a total of 18 benches, which is just basically what n is. This is our answer for n over here. So now let's look at problem number 10 from this test. 7 cubes, whose volumes are 1, 8, 27, 64, all the way to 343, are stacked vertically on top of each other to form a tower, as the volume of the cube decreases from bottom to top. Except for the bottom cube, the bottom face of each cube lies on the cube below it. What is the surface area of this tower? So the best thing to do is obviously draw a picture. So I'm just going to draw a quick two-dimensional picture over here with the bottom. This is the bottom cube. Then the next comes the top cube. Then the next top cube, and then it goes all the way up until we have a total of 7 cubes. And we see here that we can easily find the side lengths of each of these cubes because we're given the volume. And the side length of a cube given the volume is simply just the cube root of the volume, meaning that our cubes have side lengths of 1, 2, 3, all the way to 7. So in order to find the surface area of the bottom cube, what we're going to do is simply just plug in the side lengths, and it shows that the surface area of one face is 49. But there are 5 completely exposed faces. The one on the bottom, the one and 4 ones on the side. However, the top one is partially covered, and we'll get back to how to find the surface area of the partially covered cube over there. So if it looks something like this. So it's going to be 5 times the number squared. So 5 times the side length squared. 7 squared plus, and for the next few cubes, it's going to be pretty different. Because when we have a side length of 6, our faces are 36, so it's just going to be the side length squared, but we only have 4 exposed faces because the top face and the bottom face are completely covered. And we'll get back to how to find the surface area of the partially exposed faces. So now it'll be 4 times 6 squared. And the same thing applies to 5 and 4 and 3 and 2. So we can write this as 5 times 7 squared plus 4 times 6 squared plus 4 times 5 squared all the way to 4 times 2 squared. And then for 1, it's slightly different, because if we were to draw a 1, it would have 5 faces exposed. The 4 on the side and the 1 on the top. So this would be plus 5 times 1. So that's our equation for how to find this. But we still have a remaining part left. We still have the partially exposed top faces for each one of these things. And the way we can do that is kind of look at a bird's eye view. So if we look at a bird's eye view, suppose we have a cube, it's going to look something like this. So this will be the cube on the top, and this will be the cube on the bottom. So let's say we were looking at the cubes with side lengths of 6, and side lengths of 7. So it would be 36, and the outside cube would be 49. Meaning that the inner surface area over here would be 49 minus 36. And that would apply to every single cube all the way till 2 and 1. So we can add those lengths on to here as well. So that would be 49 minus 36, which is simply just 13. And then 36 minus 25, which is simply just going to be 11, plus 25 minus 16, which is 9, plus 16 minus 9, which is 7. And you can see where this is going. This goes all the way to a 4 minus 1, which is 3. And this is basically our final expression for the surface area of the tower. And when we add it all up, this should be equal to 658 as our final answer for the surface area of this tower.